On October 28, 2023, the Louisiana Center for the Book in the State Library of Louisiana presented the 19th edition of the Louisiana Book Festival. A Traveler's Guide to the Stars by Les Johnson is only one of the outstanding programs presented at this event. Les Johnson, an author, futurist, and NASA technologist, has written several science fiction novels and multiple popular science nonfiction books, including Graphene, the super strong, super thin, and super versatile material that will revolutionize the world, The Space-Time War, and Saving Proxima. His books earned him the Canopus Award and the Watkins Prize for Science Writing. In his day job, Johnson works at the NASA George C. Marshall Space Flight Center in Huntsville, Alabama, where he builds spaceships. And now, Les Johnson.
First off, I want to say thanks for having me here today, and I want to give a big shout out to all the volunteers because I arrived last night, went to the reception, everything went flawlessly. Today has just been run like clockwork, and I know that these volunteers have given up a lot of time and are doing a lot of work. So when you see them out and about, be sure you thank them, okay? Because as a guest here at the conference, they've made it painless, and it's really been great. Real quick background on myself, I am a physicist. I'm originally from the hills of eastern Kentucky. If you've ever been to eastern Kentucky, where Ohio, West Virginia, and Kentucky all come together on another river, not quite as big as the one that's here, the Ohio River, that's where I'm from, a little steel and coal community there, where I originally was a little boy, 7 years old. My parents woke me up at 11 o'clock at night to watch Neil Armstrong walk on the moon. And so I was very privileged to remember that. I don't remember much about it, but I remember they were excited. This is important, you gotta watch this. And shortly thereafter, my older sister let me stay up with her and watch the reruns of Star Trek, and then that was over. It was over. It was at that point I was decided I was going to be a scientist. Didn't know what a scientist did, but I was going to be one. I was going to work for NASA. And since everyone I saw on TV talking about working for NASA had a German accent, I thought I had to learn German. And that was because of the German rocket scientists who built the Saturn rockets that took us to the moon during the 60s. So I went to college at Transylvania University. It's a real thing. In Lexington, Kentucky. It's a small liberal arts college. And I got a BA in physics. It's one of the classic liberal arts. But while I was there, my writing desire to be a writer was further increased because I had read science fiction voraciously up to this point, still do. But when you get a BA, even in physics, you end up taking a lot of liberal arts classes, right? So I took music appreciation, art appreciation, literature, creative writing, loved all of that. Went on to graduate school in physics at Vanderbilt. Got out of Vanderbilt in the mid-'80s and moved to Huntsville, Alabama, where I was working on Ronald Reagan's Star Wars missile defense systems before it ended. And so I was, a science fiction guy building particle beam battle stations, for Earth orbit. So it was kind of cool. But my heart was always in civil space. I wanted to support space exploration. So I got an opportunity to interview for a job at NASA Marshall in 1990. And I started there at that time, and I've been there ever since. I've had a great career. Started writing nonfiction books in the early 2000s, and science fiction in the latter part of the early 2000s, right around 2010, for Baen Books. They're distributed by Simon & Schuster. One of my latest ones is The Space-Time War, which they have copies of over in the tent. It's a space adventure story, and they keep coming back for more books. So apparently somebody likes them, right? I was told never read reviews of your books, so I don't. And I was told if your publisher comes back for another contract, it means that's the best review you can have, right? It means they're making money. So the book that I'll be talking about today is one I've wanted to write since I was that 7-year-old boy. It's called A Traveler's Guide to the Stars. It was published last fall by Princeton University Press, who's an outstanding publisher to work with. I love this cover. Don't you just love this cover? I mean, it couldn't be a better cover. Wow. And this is a popular science nonfiction book that I'll talk about today that tries to explain a little bit about the challenges of going to the stars, which has been something I've thought about, like I say, since we took that first step on the moon in 1969. And I came to realize that most people have a perception of either it's so hard it's going to be impossible, which is not true. It looks like the laws of nature and the laws of physics say it's going to be possible, or they expect it to be too easy. And I think science fiction has ruined us in that regard because we thought we would have spaceships going to, the Discovery was supposed to have gone to Jupiter by now in 2001, A Space Odyssey, and found the monolith and the aliens and everything else, and it didn't happen, right? It's taken a lot longer than we expected, and I think part of that is it's a lot more difficult than we thought to go beyond low Earth orbit. It's really hard. And so I'd like to give you a sense today of the challenge of going to the stars and talk a little bit about, if I have enough time, why it's important. And if I don't have enough time, catch me around later today and we'll chat, okay? So here's my contact information, how you can reach out to me. I do have to say that I write my books off the books. NASA does not endorse my writing. I actually have to promise them that I won't do anything at work that's related to my writing, and I do it all on my own time. So I came here on vacation time to get here Friday and everything else. So it's my social media and how to reach me. So it's as difficult as it is to believe with all the news that's been in the headlines about finding planets around other stars. Until the 1990s, there was no direct evidence they existed. Now, astronomers and planetary scientists kind of knew they were out there, assuming that the Earth was not unique in the entire universe, in terms of stars having planets. But they couldn't point to data that said, we have detected one, here's how we know we've detected one, until the 1990s. And since then, there's been just an almost explosion in the number of exoplanets. But before that, I'll take a nod to fellow science fiction fans. We all kind of knew they were there. Captain Kirk was visiting them, Han Solo was going. So we knew they were out there. We were imagining what it would be like. And these are some things that inspired people and audiences I've talked to. But today, there are more than 5,000 known exoplanets. And that means that they've been detected by one method, and somebody else using a completely different physical method confirmed that. And so these are exoplanets, and they're called confirmed because they've been independently verified using two different independent methods of proving that they exist. It's some kind of different kinds of astronomy. It's a whole talk in and of itself. But if you don't have to have two independent objective measures of their existence, this number is in the tens of thousands, okay? Where there's been one method that has detected exoplanets. So, and all of these are in this little region down here that's not too far from our sun in this artist concept of the Milky Way galaxy. So, that's amazing. And I get a lot of questions. How do we get there, right? Les, you work on advanced in-space propulsion. I didn't mention this, but my work at NASA, I work on mostly something called solar sailing, which is how spacecraft go from planet to planet in deep space. I had a payload launch on the Artemis 1 last November. I was at the launch down in Florida. That was super exciting. See that big rocket launch in the middle of the night. And I have another one that'll fly in 2027, which if I'm not retired by then, I'll be thinking about retirement by then. And so people say, how are we going to get there? You work on this advanced propulsion stuff. And it really boils down to this. And I pay homage to a great, fun read or show. If you've ever seen The Hitchhiker's Guide to the Galaxy, you'll understand where I got the title of the book, A Traveler's Guide to the Stars. And this quote has always stuck with me about the distances involved in space. You just won't believe how vastly huge, mind-bogglingly big it is. I mean, you think it's a long way just down the road to the chemist, but that's just peanuts compared to going to space. And it is. But we make it look close. If you look on Google, what are the nearest stars? Of course, our sun is the nearest star. And then you'll see a map that looks something like this, where it says, oh, Alpha Centauri is about 4.2 light years away, right? And these others are out at 6 light years. Those are the close. That's the neighborhood. That's the local neighborhood. Well, yeah, but these distances are a little misleading, and let's delve into that. The Earth, the Proxima Centauri, is the nearest star. It takes light 4.2 years to cover that distance. Now, the last time I gave this talk, I was in Europe, so I switched everything over to kilometers, so I'm going to put it back in English units for y'all. If you think about the sun and the sunlight on this beautiful day we have here on the Earth is 93 million miles from the sun. Light, traveling at 186,000 miles every second, takes 8 minutes. 8 minutes to get from the sun to give you a sunburn, okay? And wow, 8 minutes. So the sun could go blink, I'm not here anymore, and we wouldn't know it for 8 minutes, all right? And that is a relatively close distance, 93 million miles, all right? On this scale, Alpha Centauri is trillions of miles away. But what's a trillion miles? Do you understand what a trillion miles? You have no idea. I have no idea. Astronomers have no idea, okay? They can do the math, They know what it is, but they don't have an experiential basis for that. Some people do. People who've orbited the Earth on the space station travel around the Earth about every 90 minutes. Who was here for the talk this morning of the woman who works at St. Jude's that went to space? You were here. I'm insanely jealous. I would love to be in the cupola and look down on the Earth. But she traveled around the Earth. She experienced traveling around the Earth every 90 minutes, okay? I have a Honda Pilot. It's got about 250,000 miles on it. I've driven to the moon, okay? In the 20 years I've had my Honda. It's an advertisement for a Honda, right? They would love that. So I experience, you know, it's taken me 20 years, lots of trips, lots of science fiction convention trips, whatever, but I've driven that distance. I experienced that. But going to the sun, I have no idea what it means. 93 million miles, 1.5 million, 150 million kilometers. So I created my own unit of measure. It's called the less measure of astronomy, and it's related to what astronomers use. They take this Earth-Sun distance and they call it 1 astronomical unit, okay? I say, let's call it 1 foot. So my heel is the sun, and my toe is where the Earth is. That's my unit of measure for distances in space, all right? So if we want to go to the furthest planet in the solar system, which those of you who are an older generation will still intuitively say Pluto, but it's not, it's Neptune, all right? And you look at Neptune, on Less's scale, it's 30 feet back, so it's about the back wall of this room, okay? And that's 30 times 93 million in terms of the miles to get to Neptune. It takes our fastest spacecraft about a decade, 10 years, okay, to go 30 of Less's feet in this new scale of the universe. On this scale, the nearest star, if every one of my feet is 93 million miles, the nearest star is 52 miles in that direction. 52 times 5,280 times 93 million. That's the closest star, okay? How are we going to do this? That is not going to be as easy as going warp factor 1, okay, and being there in, you know, a day or two or whatever it is in Star Trek. So, and that's the closest star. If you look at our galaxy and the things we want to do, there are hundreds of billions of planets probably in our galaxy alone. And unfortunately, all the good stuff's probably over here, right? So if we're going to go one of these days, we've got to figure out how to do that. Now, we are already an interstellar species. The Voyager probes, launched before some of you were born in 1977, have left the solar system and they're on their way, okay? They're not the fastest spacecraft we built, but they're among the fastest we've built. If they were pointed in the right direction, which they're not, they would reach Alpha Centauri in about 70,000 years, okay? So we are already traveling to the stars. We have sent our first robotic spacecraft out. They won't be working then, but they'll still be there, okay? I don't call that a practical interstellar trip, okay? So I'm going to define, for purposes of this lecture, a practical trip to another star as being one that takes less than 1,000 years. And that's the most time I'm willing to say is practical. Why do I say that? Because I've been to Europe. This is difficult for we people from the Americas to understand, but they have buildings that are older than 1,000 years, okay? I was also in the Middle East a year ago, and they have buildings, remnants of buildings, that make those in Europe look like recent construction, okay? So as a society, a civilization, we have records going back this far. So if we can do something that lasts 1,000 years, like some of the cathedrals in Europe, or the Great Wall of China, right? Then we can do a star voyage in 1,000 years, all right? So how do we do it? Well, if you can forget rockets, people say, oh, well, we've got, you know, these big rockets NASA's building, the SpaceX is building, that everybody's building, how fantastic they'll be to take us to the stars. Well, yeah, if you want to wait 50,000 years, we can do a little bit better than Voyager, but if you take all of the energy that's theoretically possible at 100% efficiency from chemistry, which is what we do in chemical rockets, to convert that to thrust, 50,000-year trip. You just can't go fast enough. There are these other rockets called electric rockets, which are way cool, and they're many times more efficient per pound of fuel than a chemical rocket. To make them work, just instead of chemistry causing them to work, it uses electromagnetic fields, big electric fields and big magnetic fields. If you've ever had an MRI, you've experienced a big magnetic field, and they tell you not to wear anything metallic because it'll fly across the room and hit the magnet. That's how a propulsion system that uses this kind of technology works, okay? But guess what? Even they are too inefficient. At the 100% theoretical efficiency, about 10,000 years. They go faster, but the trip times are just unbelievably long. And I hate to say it, even nuclear rockets, where we harness the energy of nuclear fission, like we have in our power plants, even those are too inefficient, and it would still take more than 10,000 years to cross those distances. Now, there are some rockets that ought to be able to take us to the stars someday. And you've heard some of these terms probably if you're a science fiction reader, or go to science fiction movies, or think about space travel. They're almost magical, right? People say, oh, we have fusion drive or antimatter propulsion. These are all real things, okay? The problem is physics says they're real, but the engineers I work with, we don't have a clue how to build these to make a spacecraft go to the stars. So fundamentally, if you get down to that 100% efficiency, which, and again, I know some engineers in the audience here are shaking their head, you'll never get 100% efficiency. But let's just assume you do, right? These could do that. And even if you get 90% efficiency, which would be really good, you could still take a trip to the stars and get there in under 1,000 years with some of these technologies. Fusion propulsion takes the energy that powers the sun, which scientists have been trying to harness here on Earth for generating electricity for my entire lifetime. The joke in the physics community is fission is the power system of the future and always will be. I hope that's not true, because I'd like to see us get fusion power terrestrially to help solve some of our energy and environment problems. But once we have it working in a reactor to produce power, we ought to be able to miniaturize it and put it on a spaceship and use it to power our spaceship. The problem is, it's only good enough to go out to the first few nearest stars. Beyond that, you can't carry enough fuel to get the speeds you need to make the trip time any shorter. And so even fusion, the energy that powers the sun, is not efficient enough to really give us the stars. The ultimate rocket, if you're going to take a rocket, and a rocket, remember, is anything where I throw something this way that makes me move this way. It's conservation of momentum. So a rocket can be as simple as the balloon that your kids blow up and then let go of. The air comes out of the balloon this way, the balloon goes that way, they've built a rocket, okay? That's how a rocket works. You throw something overboard as efficiently as you can so that you can move as fast as you can in the other direction, all right? So there's this thing called antimatter. I love antimatter. It sounds cool, and it's real, okay? The universe, in extreme energy circumstances, makes this interesting form of matter where you have protons and electrons, and you have something that looks just like a proton, has the same mass as a proton, like in all the atoms that we're made out of, but instead of a positive charge, which protons have, it has a negative charge. It has an interesting property. When you bring this proton together with what is called an antiproton, the antimatter corollary of a proton, and they touch, it goes boom, okay? And it is a manifestation of that famous man's equation right up here, E equals mc squared. If you've ever wondered, what does that really mean? I hear people say this all the time, famous equation, but I have no clue what it means. This is one of the things it means, that you can convert matter into energy and vice versa in theory, and antimatter does it in practice. Those particles annihilate, produce gamma rays, X-rays, all kinds of secondary particles at extremely high energies, and you could harness this antimatter if you can store it. The problem is antimatter touching matter goes boom, so what do you put it in, right? How do you store it? How do you create it? It's very difficult to create. The total global production in these big superconducting colliders in Europe and other places is on the order of 1/1000,000 of a gram. And I need a ton, okay? And antimatter is so dangerous that if you had a small teaspoonful and I dropped it on the floor, Baton Rouge would cease to exist, okay? I'm sorry, Karen, I would destroy your town. Don't let me have antimatter, okay? Don't let Les have it. But I will tell you, don't be afraid either. Radioactivity is all around us, okay? Go into your kitchen, and I bet some of you have a banana in your kitchen. Well, the soil that bananas are grown in Latin America are rich in potassium-40. And you've always heard you want to balance your electrolytes, get potassium from bananas, right? Well, some of that potassium is slightly radioactive, okay? And as it decays spontaneously about once every 70 minutes or so, it will give off an anti-electron, a positron, which will immediately annihilate the banana and produce some gamma rays, which will get absorbed and is done. Don't be afraid to eat your bananas, okay? Because radioactivity is all around us. It's in the soil, it's in the air. But if you have bananas in your kitchen, you can amaze your friends next time you have a party. You're making antimatter on your counter, right there. So to go to the stars, what we need is a big banana plantation. I'm kidding, I'm kidding. But it is kind of interesting. This stuff is real, it's around you, it's in everyday life, and you've probably eaten some of it, okay? So this is not just science, it's not just fantasy, antimatter is real. We just have to make a bunch of it to be able to go to the stars. So as I go quickly to the end here of the propulsion part of this, and I want to have time to cover a few other things, people say, is there another way? And I think there is, and this is where I've spent most of my career, and it's been working on something called a solar sail. Now, a solar sail is a sail, like you would expect a ship on the ocean, the schooners, the big, clipper ships, or if you go to the lake, and you're on the river here, you see sailing ships, right? And instead of the wind, the air wind reflecting from the sail, pushing on the sail, that's how it works, is the wind reflects from the sail, momentum from the air is transferred to the sail, it pulls the sail, it's got a mast that connects to the ship, and basically it drags the ship with it, right? In space, if you deploy a large, lightweight reflector, think of a big sheet of aluminum foil, but much thinner, much lighter weight, and sunlight reflects from it, light has an interesting property. It doesn't have rest mass, but it has momentum. So if you think of each particle of light, each photon of light as like a little BB, these BBs bounce off the sail and they push on the sail just a little bit. And if you're out of the Earth's gravity, you'll never get it off the ground because Earth's gravity will keep it ground bound. You can't get enough thrust with a sail. But when you get in space and you deploy these things and the sun is shining, they will move. They've been demonstrated in space. Several missions have flown to demonstrate that these work. I've been working on sails at NASA Marshall, and over my career of 20 years, these are some of the sails that we have built, and ever-increasing scale from here. The first one we flew was in 2010. It was 10 square meters, would have fit on this tabletop a little bit bigger than that. The one that launched last November was almost 100 square meters, 10 times bigger. There's one flying this fall, or will actually be next summer, called the Advanced Composite Sails System, and it's about the same size, about 100 square meters. This is the one that's going to fly in 2027. It's 16 times bigger. It is 17,800 square feet. The sail material itself looks like aluminum foil, but it's 2.5 microns thick. What that means is, those of you who still have hair, it's about the thickness of your hair, okay? And it all folds up in a box that's not much bigger than this podium and is deployed with 4 100-foot booms. Here is a picture of 1/4 of the sail deployed last fall by my team. I am the third person from the right, okay? So that is a sail. We're building it. We're going to fly it. It cannot take us to the stars, but it can take spacecraft in our solar system to other planets and use no fuel to do it, okay? And the beauty of that is, if you deploy a really big sail really close to the sun, where the sunlight pressure is really high, you can get really rapid acceleration, really, it's technical terms, right? That's why I use it so much. And go extremely fast out of the solar system. But to do that, you've got to have a sail that weighs much less than our current sails. And I did the math and figured out that if we had a sail that wasn't 1,000 square meters or 10,000 square meters, but was 1,000,000 square meters, a square kilometer, and it had the mass of only about 1 gram per square meter, which is basically 1/3 of a raisin per square meter, then you could build a sail fast enough to get to the stars in 1,000 years. And when I first started working on this plan, which you see here, we had just launched the 10 square meter sail in the bottom corner. We're now building the one that's the last of the yellow ones. Okay, so we're 2 orders of magnitude larger than where we started. But what we needed was the one on the right, which was extremely large. There was no material that existed that would sustain itself under that stress and that size. 2004, that changed with the discovery of my previous books topic, graphene. It's a super material, it's a form of carbon. It's 1 atom layer thick, strong enough to support itself under that weight. It's 300 times stronger than steel. It will revolutionize the world, and it'll let us build this big sail. Do we know how to build it that big right now? No. Is it possible? Yes. We just have to figure out how to build graphene sheets to scale, and we don't know how to do that right now. And if you want to get faster than 1,000 years, you shine a big laser on it, in addition to sunlight to speed it up to get it to go faster. And theoretically, you could make the trip in under 100 years to Alpha Centauri. Now let's assume we build this. I want to give you a sense of the energy involved in this thing. And let's assume that we get it to 10% the speed of light. 10% of 186,000 miles per second, so 18,600 miles per second. 18,000 miles per second. Okay, tell your Louisiana state troopers, catch me, right? Not going to happen. All right, and let's say you're able to accelerate this to go to the stars, okay? Now, let's say that our spacecraft is small. I like to think small to begin with. We're going to say it's a kilogram in weight, which is about the same as a pineapple. Okay, get your pineapple from the store. Think about accelerating that to 10% the speed of light. We're sending it on a robotic mission to Alpha Centauri. It's going to get there in 40 to 50 years and send pictures back of the planets around Alpha Centauri. Now you want to make sure that you have good aim. Because if you miss and you don't fly by Alpha Centauri and you hit Alpha Centauri, the energy of motion, the kinetic energy of motion of your pineapple would release an equivalent energy as 7 Hiroshima-class atomic bombs, just because it's moving so darn fast when it hit the planet. So if you miss, okay, and I'm looking at this young lady sitting on the edge over here. If you build this sail and you miss, you might start the first interstellar war, okay? We don't want to go from a traveler's guide to the stars to the space-time war in one leap, okay? So we want to be careful about this, because when you're building and you're thinking about these really fast trip times, you're thinking about things that are moving really fast, okay? And anything like that could also be a weapon, and mistakes could be dangerous, so we want to do it. Now, there are lots of other challenges. Communication. If we want to take people, there's a whole chapter in the book about what it means to take people. World ships. I interviewed people who are researching how to put bodies into like stasis they call it torpor, so they might be able to stay asleep for part of the voyage and such. That progress is being made. I don't think we're anywhere close to being able to do that, whereas if you send people, you might have a 10,000-year voyage, because a big ship like that can't go really fast. And you might have generations of people live and die on these ships. So I've interviewed people about world ship design, talked to folks about hibernation. A fellow I know who's really big into, a colleague of mine who's really into genetics research about how you might be able to alter human aging someday with the work we're doing and our understanding of the human genome. So I expect that when we finally take these trips to the stars, it won't just be people like me who've worked on propulsion. It'll be all of these things. It'll be the medical people who make us live longer and live healthier and live radiation resistant, don't get cancer. It'll be the life support people who figure out how to keep a crew alive for these trips. But as I get to the end here, okay, I got to wrap up. So I have time for questions. I want to just go into the reason why. The scientist in me says, we want to go because it's there, we want to understand it. I think that's justification enough, okay? But I also believe this statement right here. Life is good. Life in this cold, apparently dead universe, and it looks mostly dead out there, folks, is rare. We need to protect it here on Earth, do what we can to protect, preserve, and make Earth a better place than it is for life, because we're trashing it. And we also need to extend life into the solar system and ultimately to the stars, because the love you feel for your children, the music that you hear when you hear a Mozart symphony, the pleasure you get out of solving a math equation, I do, and the friendship you have sitting around a table, having a dinner and a drink with friends, those are morally good things. And life is special. It's important. It needs to be protected, preserved, and spread throughout the solar system and the universe. With all our flaws, we need to do that. Because things happen here on Earth. There have been extinction events. We could do stupid stuff to ourselves. We need to protect and preserve life here and abroad. So with that, I'll take my conclusion by telling you that the universe, and our galaxy in particular, are full of planets. Reaching the stars is not going to be impossible. I have a chapter of why warp drive won't work, sorry, or the Millennium Falcon star drive, which is even in worse shape than warp drive. Why they won't work, and that's unfortunate unless there's a new physics, which could always happen. But reaching the stars, based on what we know now, is possible, all right? The question is, are we up to the challenge? Are we going to get to the point where we look back on our home world and our sun is just another star in the sky? That's what one of my visions is. And with that, I'll stop and take questions. Yeah.
So when we get to this point when we have these solar cells that would allow us to do these really quick trips, what does physics say about how we would have to slow it down, because we don't have like water to slow down like we do with a sailing ship and dropping the sail?
Well, the beauty of a sail for the first few voyages, I think they'll strictly be just fast flybys. That's my pineapple. Going really close, taking pictures and sending the pictures back. But if we get back pictures that say, hey, this looks interesting, we want to go and you get more information and maybe send people. If it's a solar sail and not a laser sail, you could do a close flyby of Alpha Centauri and use the sunlight pressure from that star to slow down, like you used it here to speed up. Now, if we use a laser to get it going faster, that's a problem, right? Because there won't be a laser waiting on you there to do that. So you might be able to slow down, but you might not be able to capture. Another idea I've heard is you throw overboard a 1,000 kilometer long, one atom layer thick graphene wire that also interacts with the magnetic field of that star and uses the sunlight as a brake and the magnetic field as a brake. For those of you that I'm spouting gobbledygook, you may have played with magnets, right? And when you put two north poles of a magnet together, they repel. You can create a magnet with this wire, and when it gets close to a star which has a magnetic field, it would repel. It's like putting two north poles of a magnet together and they push against each other. So you use the light to slow down, throw this big wire out, which would be like a big magnet bouncing against a magnet. You might be able to slow down and go into orbit. Might. You have to be really good. But it's possible. Yeah, it's possible. Other questions? Yeah.
You know about sending the images back. So I'm curious, how long, in theory, would that take? Are they going the speed of light, so they wouldn't take as long?
They're going the speed of light, so you'd get the 4.2 years. That's right. You'd wait about 4. But you know, if I've launched this thing on a 1,000-year voyage, I'm going to wait another 4 years. And you know, people ask this question about having to have patience for all these things. One of the other things that impressed me about the Great Wall of China, not having seen it but read about it, and the cathedrals in Europe, is that they were started by people who knew that project would not be completed before they died. But they felt like they had a grander purpose to work on it. And so generations of people, the Great Pyramids, generations of people worked on these things, right? And so, yeah, it's an extra while to wait, but I think it would be worth the wait.
I guess that was my question. And the other part of that is, do we have the technology to send it back that far? I know we're getting images from other space satellites, so to go that distance, do we have that technology?
We know how to do it, like we know how to do some of these propulsion systems. We just don't know how to do it well enough to engineer it yet. There's a fellow named David Messerschmidt, who's a professor at University of California, Berkeley. This has been his specialty. And he has figured out how to do some really clever things with light to send optical signals back that would contain the data at very low intensity light across those distances. So I think the answer is physically possible, which is great, but the engineering challenge is there, just like on the propulsion. How do you do that, really, okay? But we're making progress. You know, if you'd gone back to the Wright brothers, and I recently was in Ohio near Dayton, where I saw their shop where they were building an airplane, and you go to them and say, is flight theoretically possible? They're going to say, oh yeah. And then you say, okay, design me a 777. How do you do that, right? But they knew it was possible, and they took that first step. So that's what I'm thinking we ought to do here. Yeah. Other questions? Yes?
Do you have a favorite sci-fi book or movie that inspires you?
Okay, that's a question I get some. Favorite book, anything by the author, and this is my generation speaking here. I was so inspired by anything written by Arthur C. Clarke. He was, in my generation when I was young, he's the greatest writer out there. Today, of the newer crop, still a little older, Stephen Baxter, He's getting a little long in the tooth in his writing. And of course, Les Johnson. In terms of other writers, yeah, I think there are, but I'd be hard-pressed to give you a list because there are so many that I find really good stuff. I'm very entertained by a lot of thoughtful historical analogs in space, which teach us about how civilizations and our society might behave in space that aren't really technical. And I would say the writings of David Weber really do that for me. He's a historian turned science fiction writer, and he posits plausible cultures and clashes of cultures in space that I find fascinating. Now, in terms of movies, did anybody see Passengers? Yes. I'm a sucker for a good love story, okay? And that movie inspired me because it speaks to this thing I talked about, life is good and love is good. And that was one of those stories where you have this sterile environment of a deep space mission and rules that have to be followed and all this, you know, cold, sterile interstellar voyage stuff, and then two people found love. And that just tugged at me here. I guess that's because I'm maybe that phase of life, whatever, I don't know. But it just really tugged at me. So I would recommend seeing that movie if you haven't seen it. It was not the best hard science fiction movie, but it's an affirming movie in my opinion. Yeah.
Could you comment on the time dilation issue?
Oh yeah.
1,000 years that it would take to get to the star. How many years have passed already?
Oh, about 1,000. You're not going fast enough to get really to that. You have to get way above a significant fraction of the speed of light, even higher than that 10% for it to be a significant thing. Travis Taylor and I are writing a series of books. First book came out too long ago without the sequel yet, but we're almost finished. I'm pointing over here because he was giving me a hard time about not having the book out yet. The first book's called Saving Proxima. And I think you'd be entertained by that because we deal with relativistic differences between two ships launched at slightly different times at different speeds going to the same destination. And what happened back on Earth with their clock, ship A's clock, ship B clock. I had to build a spreadsheet to keep track of what was happening when with all of the changes in the rate at which time passes when you go close to the speed of light. It's a fun problem. It's more than I can go to in this talk. It's about something called special relativity. Bottom line, if you're not familiar with that, is nature's weird, okay? And if you take you and you stay here and he gets on a ship that's going 98% the speed of light, time passes at a different rate for them. And so he'll get there and think it's a certain year and she'll say, no, it's a different year, right? So the rate at which time passes changes depending on how fast you move. And it's real. It's been measured actually on the International Space Station to within microseconds. It experiences the rate of time passing a little different than we do on the ground. But it's not enough to make a big deal. So even a 1,000-year trip, it would not be significant. If we were traveling at real close to the speed of light and we went to 4.2 light years in 6 years, yeah, it'd be a big deal. Yeah, it'd be a big deal. Yeah.
It sounds like a lot of what we need involves a lot of long-term growth.
Yes.
Like people on top of people. But I know also over the last 50 years, our interest in space has grown and waned. And is that why more private interests are the way to go? And what can we do as normal people that don't know all this brilliant stuff? What can we do to try to help keep interest alive?
Well, the latter part, I'll tell you what you first thing to do. Look up a group that I volunteer my time with, if I can get to the slide, the Interstellar Research Group. And we had our 8th meeting up in Canada this year, and it is a group of people who are passionate about going to the stars. Not all are scientists and engineers. We have science fiction writers. We have space lawyers. Yes, there's a thing, space law, okay, who are a part of this. It's an all-volunteer organization. We meet about every 2 years. Basically geek out for 3 days with technical papers and papers about latest trends in space law and treaties. We have people come in and talk about, suspended animation and the latest research there. We have biomedical people coming in. We have art shows. We had this past meeting, we had a woman who was the consultant for the movie Arrival. She was the one who was the model for the linguist who was in the movie. She was the actual scientist who they modeled that character after. So we think a lot about these things, and our next meeting will be in 2025 in Houston. are actually College Station, Texas. And there might be a meeting next year. We're working it real hard, our first European meeting in Luxembourg. So we're working that pretty hard. But it's a way to get involved, and volunteering time. They have membership structure. We have podcasts and recommended readings and things like that. Now, in terms of private space, they do it for money, okay? And so I think it's great because it's reduced launch cost. NASA's dollars can now spend more money for payloads, not as much for how much it costs to launch things. A lot of people don't know this, but NASA has not paid for the launch of robotic rockets since 1988. SpaceX did not invent commercialization of launch. They invented commercialization of human launch, okay? Robotic launch, Lockheed Martin, Boeing, those companies have been launching for the government, most of, before I started my professional career, they were doing that. SpaceX and Blue Origin have changed the cost model. They've unleashed the creativity of people who want to make a lot of money. And that makes it cheaper on people like me. And so what can you do? Just advocate for science and technology research in every way with your congressional people. Here in Louisiana, you've got a powerful new voice in Washington, right? Whether you like his politics or not, he can advocate for good science funding, which is typically bipartisan, right? So you can do that. Fundamental science is important. It's how we're going to get the breakthroughs. So that's what I think you can do. So go do it. Okay. Yes, sir.
Moving that fast, do we have to worry about fender benders?
You do. Yeah, you do. There's a lot of dust out there. There's about 1 atom per every cubic meter in interstellar space, but there might be a piece of dust in that cubic meter. And if you're traveling at 10% the speed of light, that's going to be like driving in your car and have somebody drop a boulder toward you, right? So there'll have to be shielding, et cetera. There are people think about how you would survive that. Whether you blow it up before you get to it, you divert it with big lasers, whatever. So there are people trying to work that problem. The way I get around it is statistics. I want to launch 1,000 probes to Alpha Centauri and hope a few get through. No, really. I mean, you play the odds, right? And so, I think if we make them cheap enough, which I think in the future we can, we just send a whole bunch of them, and some of them will get through. Yeah. Yeah. Yeah.
Well, he kind of stole my thunder there.
Oh!
If you want, well, maybe a short shower. But the practicality of traveling through the interstellar medium kind of interests me to some extent.
Right.
I know about traveling in Earth's atmosphere.
Right, right.
Velocity versus density. And eventually your thrust of your propulsion system runs up against the drag.
It does. That's correct.
Now, even the ISS has to occasionally be boosted, because even at its
240 miles. It gets about a Newton of continuous drag.
Still running into enough air.
It is. That's right.
Running into enough drag that it needs to be boosted.
Right.
Have the Voyager probes given us any idea of the density of the interstellar medium?
They have dust detectors on them, dust detectors, and they actually can count impacts with dust grains. Most of our deep space spacecraft have those these days, so throughout the solar system we know what we have. And I've been given the red flag of death, which means I need to shut up. So at this point, let's follow that up. Hang around. I hope you all are going to be around a little bit. Let's follow that up. The answer is spacecraft traveling through deep space, they will experience from this 1 atom per cubic meter a little bit of drag. It's not going to be enough if you're traveling at these speeds to make a huge difference. I'd be more worried about hitting a dust grain than I am from the total pressure of the drag going through the interstellar medium. And you can account for that in your thrust. And we have a pretty good idea of what it is because we look along the line of telescopes and there's something called a column density. And you can get that by estimating how much light has been absorbed or scattered by particles on a line of sight between you and the star. So you can get a kind of an average density and you can build that into your launch profile so that you can overcome that before you get to the destination.
I think a lot of this is a question of scale.
It is. It is. My answer is just the bottom line, okay? And I know I really do have to get off. Two takeaways. Traveling to the stars is going to be really hard, but we can do it, but we got to think big. Big energy, big vehicles, think big, because we won't be able to do it on the cheap and small, right? So it's going to be hard. It's not impossible. We can do this. And with that, I better stop. Thank you all very much.